The Hyperwebster is an idea of an infinite dictionary that contains not only every English word, not only every possible pronounceable word, but every string of characters that could possibly be made from the letters in the alphabet. Like many others, I first heard about this idea in a fantastic Vsauce video about the banach-tarski paradox. In that video, it's used as an example of a self-similar collection, where portions of it are equivalent to the whole thing. In particular, considering all the words that start with A and removing the initial A, the entire Hyperwebster, including strings of all letters, is the result. This is how it's usually described. Here, you can see the first elements are A, and it's so on to it. It seems the idea is that it contains every finite string of just A's, after which comes AB, then ABA, and ABAA, after which comes every finite string of AB followed by A's. Then the same with C, all the way down to AZ, AZA, and so on, and so on. And then for B, C, all the letters in Z, and all the finite strings are supposed to be represented here. Now, you can kind of get the idea of what they're going for, but there isn't really much to go on here. The ellipses here indicating and so on and so forth and repeat this process, there isn't really enough of the process to really know how it's meant to repeat. Um, so, as a big fan of infinite ordinal numbers as a way to describe the structure of infinite collections, I wanted to try to assign one to this collection. Unfortunately, I encountered a problem almost immediately. Ordinals can only be used to describe well-ordered collections. So, what is the ordering here? Well, the natural first thought that one might have, as did I, is alphabetical order. The problem is that the standard alphabetical order is not a well ordering. If you're considering all possible finite strings here, then after you've gone through all the A's, what comes next? To use alphabetical order, it wouldn't be AB, because preceding AB would be AAB, right? In the alphabetical order, you compare the first letters, and if the first letter is the same, you compare the second letter. And A comes before B, so AAB comes before AB. But even before that would come AAAB. And so you would want to kind of extend this out to the left here, but then the problem is that this portion of the set does not have a first element. So, and that is a key criterion for a collection to be well ordered. So this is not. So if I want to talk about the order type of this entire collection, which I very much do, I will need to impose my own ordering on it. I propose the following ordering, which I will use to construct a collection which I will call the reduced Hyperwebster, because it might not actually represent the entire collection inferred to over here. So, what are the rules I propose? The first element in this reduced Hyperwebster will be the empty string, which I'll write as just the underscore character. That will be the base case. The whole construction will proceed as follows. Now we're getting some real math terms in here. Given a previously constructed collection, HR, that will follow this ordering, consider the first letter of the alphabet, alpha, which will usually represent A, but if not A, then B, and if not B, then C, and so on. Consider the first letter that could be appended to some element H of the set HR, such that H plus alpha, where the plus just denotes ordinary concatenation, is not already in HR. Identify the first H for which this is possible, and the element H plus alpha will be the new last element in HR union with the set containing that one element. All that is basically to say that this element, which you'll describe here, will be the new last element in the order, and the collection will be one larger after that. However, importantly, the empty string can only be the element H chosen for this process if no other H will actually yield a new H plus alpha element not already in the set HR. So let's look at some actual examples of this and see how this goes and what happens. So the first element here, obviously the empty string here. That's stated explicitly. That's the base case. And now, in order to get any more, you have to apply this rule here. So the previously constructed collection, that will just have to be this. That's all we have so far. So the set containing the empty string is the set HR. It does follow this ordering. It is simply the base case. So now, consider the first letter of the alphabet that could be appended such that that new element is not already in HR. Okay, so we're supposed to consider the first letter of the alphabet. So let's try A. Does A work? Can A be appended to something in this set to create an element not already in this set? Well, obviously, right? If you append A to the empty string, you will just get A. A is the first alpha for which this is possible, okay? And the empty string is the first H for which this is possible. So the empty string plus A, which is just A, will be the new element of the set. And the empty string is allowed to be chosen for this because there are no other elements in this set here that could work for this. In fact, there are no other elements in this set at all. And so the next element is A. Okay, so now if you consider the set of these two, okay, so you're supposed to consider the first letter alpha that could possibly be appended to create a new element. Okay, so A is going to work again. You can see that if you add A to A, that will give you an element that is not yet in here. Now you're supposed to identify the first element in here for which this will create a new element. It's not going to be the empty string because we've already done that. You add A to the empty string, you get A. A is already in here. So you add A to A, you get AA. And now I think the pattern should be pretty obvious. After this, you consider the set of these three, and the first letter that you could add is A. The first element you could add it to is AA, and so the next element will be AAA, and so on. It will produce all the finite strings of A's, just like we had as the first elements of the original Hyperwebster up here. So that's a good sign that the reduced Hyperwebster will be at least somewhat similar to the original one. It's starting to build out the same looking thing, except for this weird little empty string in here. But I think its inclusion is going to be worth it overall, just for the relative elegance of this rule. So, okay, we have our infinite list of finite strings of just A's and the empty string. So the first part of this collection is just this list of all the finite strings of A's and the empty string at the front. So if we're going to talk about the order type of the whole set, we'd better start pretty small and just look at this. So what is the order type of this set here? All of these things. Well, you should be able to see that there's a nice and easy way to pair up each element of this set with a natural number in the following way. You just pair each element of this set to the natural number corresponding to the number of A's in the string here. So it'll be 0, 1, 2, 3, and so on. All of these are going to be represented because each one has exactly one more A than the last, so it'll you'll always be able to find a natural number to pair it with, and each natural number is going to be represented because for every natural number, you are going to be able to find a string in here with that exact number of A's. So if you know anything about infinite ordinals at all, you will, of course, accept that the order type of this set is omega. Get this in here, yeah. The order type of this set is omega. If not, then You probably haven't watched that Vsauce video I mentioned, and it comes very highly recommended. But if you accept that this set has order type omega, you should probably accept that this one also does. Okay, so not really thinking about this comparison with the natural numbers anymore because it is very quickly going to become impractical. What is the next element in this construction? Well, okay. Let's think about what would the next element of this construction be. Well, let's go back to the definition here. Consider the first letter that could be appended to some element here to create an element not already in here. Okay, well, is A still going to work? It's not really going to, because no matter which string you pick in here, this ellipsis, this means this has gone on forever. So for any string of length, I don't know, k, then the string of length k plus 1 will have already been constructed. So appending an a to anything in here is not going to yield anything new. All the strings of a's are all already present here. So you have to consider b. Okay, so you've identified, in this case, the alpha is now b. Okay, what is the first element in here that you can add a b to create something new? Well, the very first element would be the empty string here, and the empty string plus b would just be b. But because of this last clause up here in the construction that I defined, the empty string is excluded from this privilege for now. And the reason that that this is the case is that I want this to look as close to the original Hyperwebster as possible. And if you allow the strings to start with B right after this, you will have skipped over all of this part of the structure here. So, because the empty string can only be chosen for this if there are no other elements that will yield a new element, it's not time yet for this to have a b added to it. So instead, you consider this. And if you add a b to a, you will get ab. AB is not in this set yet, so this will be the next element of the construction here. Okay, but now that we have this, if you add an A now to this, if you consider now this whole thing, this is now the previously constructed collection that you'd consider. Adding an A to this will again give you a new thing. So ABA, and then ABAA, and so on. Just keep adding A's to this, and then you'll have exactly what is represented here. All the strings of AB, and then ABA, ABAA, all the strings that are AB followed by a arbitrarily large number of A's. Here's where it is going to be different. Because if this up here is meant to be the order, then you would think that a C should come next. That is not part of an ordering that I was able to make sense of. So according to this, which is extremely specific and explicit, and I hope consistent, at least self-consistent, what would be the next thing here? Well, okay. For the same reason that you can't add an A to anything in here and get a new thing, you can't add an A to anything in all of this and get a new thing either. Every element here has already had an A appended to it, so you have to consider a B again. So the first element in this whole collection that has not yet had a B appended to it, except for the empty string, well, okay, the empty strings, it's not time for that yet. A, it's already been done, so the next one would be AA. So the next part of this collection would be AAB. Okay. So now let's pause and think about the order type again here. Here you have an infinitely long sequence of elements followed immediately by another infinitely long sequence of elements followed by a single element. So the order type of this entire thing would be omega for this infinite sequence plus another omega for this next infinite sequence, and then plus one for this little last guy out here. And now this will become uh, omega times two, of course. That ought to look pretty familiar to anyone who knows any arithmetic at all, except that in the wacky world of ordinal arithmetic, you cannot write this as uh, 2 omega like this. This is wrong. 2 omega is actually just the same as omega. For more info on that, there's other resources that I can provide that I enjoy immensely. But the upshot of this for now is that the order type of the collection so far is omega 2 plus 1. Okay, let's keep going. If you can see the pattern here, you should be able to know that what comes after AAB is AABA, followed by AABAA, and so on, like all the A's that are going after. Okay, and then what comes after this? Okay, so I'm going to now reorder this to make it a little more clear what's happening here. So the empty string is going to get its own line because it's very special. But now, so we have this row that are all the strings of A's. Then the next row is all the strings that are AB followed by any number of A's, and then AAB followed by any number of A's. The next element here that has not already had a B appended to it would be this one, AAA. It's already happened here, that resulted in this. It's already happened here, that resulted in this. And this is explicitly excluded from this privilege so far. So the next one would be AAAB, and so on. Then an infinite chain of A's being added onto this, one element at a time, one A at a time. Then after that, it would be AAAAB, and then all of its A's being added. This would come from an element here that is not pictured, but I'm sure you can imagine it's just AAAA. It yields this, and then this yields its entire thing. So now, at this point, there are 5 well-ordered, infinitely long sequences of elements. So this has order type omega times 5. Okay? Each infinitely long sequence of elements represents another omega worth of order. So you can imagine even this process now continuing. Okay? Here, the order type was omega. Here it's omega times 2. Here it's omega 3. After this, it's omega 4. After this, it's omega 5. And after repeating even this an arbitrary number of times, and then elements in here are going to look like AAA, a lot of A's, and then a B, and then an A, and then a lot more A's. Or no, wait, yeah. This would be the first one. The first element in this column here is a lot of A's preceding a B. And then the next element would be a lot of A's, and then the B, and then a single A. And the next element would be a lot of A's, and then a B, and then a double A, and then so on. And this whole thing will represent, we'll have order type omega times however many A's are here, I guess minus 1. But after this entire process, you have omega, omega 2, omega 3, and so on. Just like the limit of 1, 2, 3 for all the natural numbers was the ordinal omega, the limit of omega, omega 2, omega 3, omega 4, and all of those numbers will be omega times omega. All right? These numbers that are being multiplied by the omega here are themselves converging to another copy of omega. And so omega times omega is written nicely as omega squared. All right, and now we have our first other big like leap of logic here. We've gone from omega to omega squared. Okay, and we haven't even introduced the letter C yet, so we can start to see this might be getting pretty large in order type. But of course, let's keep going. Put this off to the side here, and move on. So what comes next? If you consider this entire thing, it might not be as obvious anymore, but you still can't add an A to anything here and get something new, right? All that is taken care of in the extension of each row. And even now, considering B, you can't add a B to anything in this entire row anymore and get anything new. All the results of that are represented down here. Everything in this row has already been extended with a letter B. So, what is the first thing that can be extended with a B in this set? It's not time for the empty string yet. It's this one here. And so, down here will be A, B, B as the next element. And then the order type of this collection will be omega squared plus 1. Now that there's one more element out here. And then it'll have its ABBA, ABBAA, and all of those things that are the same kind of stuff that we got up here. And then, after this row, the order type will be omega squared plus omega, because there's one more new infinite sequence here. Then, the next element that doesn't already have a B appended to it in here somewhere is this one. And so the next will be ABA, and then B. And then ABABA, and then ABABAA, and so on. There will be more and more A's now added to this. Okay, and that will fill out this entire second row here. We'll have a bunch of B's added to it. Every element in this row is also going to have a B added to it, just like adding a B to every element here eventually constructed this entire thing. Adding a B to every element in here is going to construct another thing of the same size. And elements in here are going to, or rows in here are going to look like a large number of A's followed by a B, and then what happens? What's the pattern here? Here it's ABB. Oh no, excuse me. I'm getting this wrong. It's important to write down these patterns correctly. I was making mistakes like this a lot as I was just making notes trying to figure this out. So let this be a cautionary tale. The pattern here is the number of A's in between these B's is increasing. So, like each element of this row starts with AB, each row in this column will be an element that starts with AB. And the number of A's in between these B's is increasing. So a row down here will look like a lot of A's, and then it's B, and then A, B, A, a large number of A's, and then the B, and then an additional A, like one more time here at the end, and so on, and so on. And then there will be a whole nother block like this that is built out down here. This one had size omega squared. And this one appropriately has size. If I can get it on the same page here, that'd be nice. This one will have size omega squared times 2, because there are 2 copies of this entire block here. So there we go. After this, it's omega squared. After this, it's omega squared times 2. Okay, so now we have extended every element of this row with AB. It's time to start extending each element of this row, and the same kinds of things will apply. So I'll do just a few, but then we can hopefully see what the pattern is going to be. All these elements up until here, until this one, have been extended with a B already. And so the next element in this big construction will be AAB copied with this and with AB added to it. And then it'll get its A's, AABBA, and so on. And then the next one will be this extended with a B, AABA, B, and so on. And elements in here are going to look like AAB. Let me actually indicate this. It's getting hard to fit all of this on one page. Here, I think we can abandon these on the previous page for now, for the sake of getting all this on the screen. So this is this element. It needs a B added to it. Or no, sorry, I've done that here, and then this one and this one, and rows that are way down here are going to look like they start with AAB. Like every element in this row starts with AAB. Every row in this column will have its first element starting with AAB, and then a large number of A's, and then a B, and then it continues on adding A's onto this, and then it continues on. Okay, and after this, the order will be, I'm just going to copy it now because it really is the same kind of structure. It's kind of it's almost a deep mathematical fact that you can just copy and paste these things. It'll be omega squared times 3, except that the 3 made it up into the superscript. Yeah. Okay, and now maybe you can imagine even continuing this whole process. After that, or after this block, now the fourth row up here will need to have a B added to each of its elements. And then after that, the order will be omega squared times 4. And then each element in this row will need a B extending each of its elements. And after that, the order type will be omega squared times 5, and so on and so on. And you can imagine every row in this first omega squared sized block up here having a B added to it, and then the chain of A's that results. And after all of that, I don't know how many ellipses are appropriate to indicate this, but I'd say at least 3. 3 sets of ellipses. This is a long process. And so the limit of this is omega squared times 2, omega squared times 3. You might be able to see that the limit of this is omega squared times omega. Let me grab grab an omega here and get it out of the superscript. All right. Omega squared times omega is better known as omega cubed. Okay, so now observe something interesting here. This is getting pretty difficult to parse, but the structure of this is now kind of three-dimensional, right? So if you think of each individual element, like this one, or even this big one down here, this is one element. If you think of each element as being like a point, then an infinite sequence of them like this is kind of like a line, which is a one-dimensional structure. That that one-dimensional structure has order type omega, also known as omega to the first power. Um, so and then if you consider many of these line-like rows as filling out this kind of square or plane-like array or matrix here or block, whatever you'd like to call it. I'm gonna give a special like name to these later, but that's not quite time for that yet. Um, but these are a two-dimensional kind of structure. They extend out forever horizontally. Horizontally, they extend out forever horizontally and also vertically. If you combine both those into one word, you get horizontally, apparently. And this, in in an appropriate match with its sort of two-dimensional structure, has its order type omega squared. And now, if you consider a lot of these square or plane-like structures kind of stacked on top of each other, obviously here they're written each one like below the next, but and so you'll have to kind of use your imagination a bit. But if you are familiar with your geometry, a lot of squares, in particular, an infinite amount of squares or planes stacked up like this is what forms a cube or the full 3D space that we all know and love and live in. And appropriately, the order type of this is omega cubed. And where did this come from? A jump from an omega sized structure to an omega squared sized structure came from continuing the construction until you had extended every element up here with a b and the a's that went along with it, right? And you continue the construction with its rule I described up here with its math symbols that you may or may not know, but you don't really need to know if you trust me that I've formulated this well. Then continuing this until every element here has been extended with a b, that resulted in all of these, and the order type went from omega to omega squared. Now, considering all of this and continuing the construction until all of the resulting collection, all of these have now been extended with a b. That results in all of this, that the order type jumped from omega squared to omega cubed. And so, if you believe me that this pattern holds, um, then then perhaps if you were to continue the construction until everything here has had a b appended to it, then you might believe that the structure would be kind of like a four-dimensional thing, and that its order type would be omega to the fourth. But let's consider at least one more element here, right? So after this entire thing, here there's a lot of ellipses here that are representing a huge continuation of the construction. What comes after this? Okay, well, we're considering now this as our whole collection that we want to extend. Okay, can an A be added to anything in here? Well, I hope you believe me that indeed it cannot. All of this is representing things that are like these rows that have all had the A extended to them already. Okay, well, can a B be added to anything in here and give something new? Well, yes, but not from this block up here. Everything in this block has had a B extended or has had a B added to it already, and that is what created this big jump of structure down here. So if we want to get a new element, we will have to go forward all the way to here, and this is the first element that has not yet been extended with a b, other than the empty string. That's very special. So A, B, B, B will be the first element of the next part of the structure. And now if you consider this, this whole thing has order type omega cubed plus 1. There's just this one little guy out here that comes after all of this stuff. Then there's this guy. He gets the plus 1. And so then you continue this all the way down and all the way down and all the way down and more of the same kind of structure here. And if you can see this pattern kind of continuing, then you might accept that if you continue it until a b has been added to everything in here, all the way up until it was omega cubed, then the result will be a structure of order type omega to the fourth. Okay. Let's now. I'm afraid it's pretty well beyond me to prove the pattern that I'm kind of noting here. I'm not that good at set theory. I'm not that good at ordinal arithmetic. I'm at best an amateur mathematician. Probably shouldn't even be considered that. I just like math as a hobby. This is something I did for fun. But gosh darn it, I saw this pattern. I continued it. I believe that it holds in accordance with the definition that I've described of here, of which I am quite proud. So I'm going to keep going, and we're going to see how far this goes. We haven't even introduced the letter C yet, and this is getting more and more. So we're almost there, though. We're almost there. So if we continue this pattern just a little more, then there will be some more things here, and then a huge block of structure with order type omega to the fifth. And then if you take all that stuff of order type omega to the fifth and continue the construction until every element in there has been extended with a b, then, if you believe me, we don't need it to be a superscript. Again, we don't need it to be a superscript. Come on. There. Do need this to be a superscript. If you extend everything in the omega to the fifth size block, then you will get an omega to the sixth size block. And if you take everything there and extend it with a b, then you will get an omega to the seventh size block, and so on. And now even the ellipses are part of a superscript. Okay, after all that, if you imagine continuing that process an arbitrary number of times, an infinite number of times, what will the structure look like? Well, the pattern in order type here is omega squared, extend all of that, omega cubed to the fourth, blah, blah, blah. The exponent on omega is increasing in accordance with the natural numbers, so the limit of this process will be omega to the full-on omega if it wants to behave and go in the superscript. Okay. How does this look? There's a lot happening here, but I believe it's all well described, here by this. Okay, so what comes after this? If we want to consider all of this stuff all the way up until the very beginning here, if we want to consider all of this and want to extend now this, now what happens? Well, I hope you'll agree that by the time we even got out to here, we were pretty well beyond adding A's to elements individually. right? Like even by this point, we're already saying, okay, like this one got a B, and then all the A's here, and then the next one got a B, and then all the A's here. All right, and then all this was the result of applying B's to everything we had before and describing a much larger thing. Here, I'll actually highlight some examples. So, applying B's to everything in here gave a much larger structure. Applying B's to everything in here gave a much larger structure all the way up to here. Applying B's to everything in here gave a far larger structure out to here. And we imagined repeating that infinitely. So each step of that process was extending a B onto, or, well, I'll be more precise here. It was continue the construction until you have extended a B to everything in what you've had before. And that created the next bit of structure that had order types with omega to the powers of these natural numbers. And the limit of that, omega to the omega, what does that mean for extending things in B's? If you imagine taking this set here, or the collection of this order type that we have constructed in this way, is there anything left in here that you can extend even with a B? Right? If this structure was built up by repeatedly applying a B on the end of everything you had before, then surely not, right? If you pick any one element in the collection of this order type, well, then it at some point it must have had this iterative process applied to it, right? That's how this is defined. And so now nothing even in here can have a B added to it and give anything new. All the elements in here, all these have already had a B applied to them, and they are all in this collection already. Except for one thing, the empty string. And now, finally, now that everything else in here has had a B added to it, now, finally, this is allowed. The empty string can only be chosen for this if no other element H will yield a new element. This is finally the case. So, the next element here will be, it should not be a superscript. It will be the a string of length 1. It's just the letter B. All right, and then after that, oh man, after that it's just BA, right? And then BAA. And in fact, this entire thing will repeat one more time. Imagine adding a B in the front of everything here, right? Like applying the actual construction means adding things onto the end of elements that have previously been built. But now if you imagine adding a B onto the front of everything here, that is what this whole thing is going to be. There's going to be a whole lot of and so on, and so on, and so on, and so on, and you'll get a whole nother copy of this, of the collection of this size. And so, at the end of all of that, the size of the collection will be, well, two copies of it. Omega to the omega times 2. Okay. And now we have all the B's. In fact, I believe that in here is every finite string that can be made of A's and B's, right? And here is why I believe that to be the case, all right? We have definitely A and B themselves, right? It's pretty clear. A is in here. It was the very second element of the whole thing, and now B is in here. It's the omega to the omega plus 1 element of this entire thing. And now is if you consider like is AA and AB and then BA and then BB, are those in here, right? Like all the combinations of size 2 are they in here? Well, yes. And not just because like you can see most of them in here, but the reason that they are definitely for sure going to be in here is that the process of constructing this collection is adding every possible letter onto the end of every possible element at some point, right? This all doesn't happen in order because, well, it doesn't happen in alphabetical order because alphabetical order is not a well ordering. But all the strings that start with A and contain A's and B's only are up here, and all the strings that start with B and contain A's and B's only are in here. And I really do think that's the case because uh, obviously all the strings of length 1 are here. All the ones of length 2 are going to be in here because they will have been built by extending the strings of length 1. All possible finite strings of length 3 are going to be in here because they will have been built by extending the strings of length 2. And in general, any finite string of length k of just a's and b's, of course, are going to be in here because they will have been constructed by appending an a and a b to all the strings of length k minus 1 in general, right? So I think that this has done a pretty bang up job of reproducing the intent of the Hyperwebster up here. Obviously, how it's originally described, there are things that go all the way to Z even before you get to things that are starting with B. But that's not in the order that I've defined. And I think the order that I've defined is going to get there eventually. It's going to get to everything. It just goes in a different order. It goes in an order, unlike this, which is not very well ordered. So, okay. Now, what comes next after the collection of this size? Well, all the things that you can have an A added to have already been done. All things you can have a B added to, all that's already been done. It's finally time to add a C to something, and that'll be our next element after this. Okay. So, going all the way back to the start. That's the very first thing that you can extend a C to and get a new thing. Well, obviously, if you add a C to anything in here, you'll get something new because up until now we have not seen a C. So again, the empty string doesn't count yet, but this nice element up here is a good candidate. So a C is the new element. It is the one that is first in order, and C is the letter first in order that can be added to something to create a new element. So this will be the new element here. And now you might think, okay, well, there's a few more examples. Okay, well then ACA, right? Is next. So then ACAA. I'm not going to do this for much more because it's going to start to kind of like lose the point if we are in the weeds of this for the whole time. Then you kind of lose the forest for the trees, as it were. And so we're going to be talking more about the grand structure of the whole collection here. So let's look at that. Let's look at that. And just this one element now is introduced. It'll kind of act eventually as a new like root point. And now all of this is going to happen again, but with an AC at the front. All right, it's not going to happen right away because the thing that comes after AC is ACA, and then a bunch of other stuff. But eventually, all of this stuff is going to happen again on AC. Okay. It's a little hard to think about now, but the rule of the construction that I defined, I'm pretty darn sure is is going to guarantee that, right? Eventually, you're going to get all the strings that start with AC and then continue in A's and B's, right? And all that's going to happen because, well, if you have AC, eventually you're going to append A to it, and at some point after that, you're going to append B to it, and then out of those two, you're going to append A to each of those and B to each of those, and so on and so on and so on. So all this is going to be repeated eventually out of just this one element here. So, even if you do believe that, it's 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 hard to kind of get there because that's not what the very next thing is, right? We have ACA and ACAA, right? Like, how do these things go in order? Well, let me try to describe that in a little more detail. Now we're going to think about continuing this construction in much larger leaps. All right, because everything that we've built all the way out to here, all the way out to the collection of size omega to the omega times 2, eventually all of them, each element here is going to need a C added to it, right? Eventually, we are going to run out of things to add A's and B's to here, and we're going to need a brand new element with a C. It's going to be this one. And then we're going to do a whole nother thing of size omega to the omega. It's not going to be the full omega to the omega times 2 because the empty string is not going to come into play again for quite a while. But eventually, all the elements here, all omega to the omega times 2 of them, and I know that's not quite right because this number is not really an amount, it just represents an arrangement, right? But it's still helpful to think of it in this way. So all omega to the omega times 2 elements, that's not quite right, um, are going to need a C added to it eventually, each of which are going to need a whole nother omega to the omega arrangement of elements tacked onto the order. And by the time each element here has had its C extension, that's how I'm going to start referring to this. By the time this whole block here, everything here has been C extended, you will have omega to the omega times 2 arrangement of elements, each of which needed an omega to the omega arrangement of elements tacked on in order to complete the construction. That sounds like multiplication to me. So, here, omega to the omega times 2 original elements here, okay, times omega to the omega. This will be the size of the collection after everything up to here has been C extended. And now, due to some funky properties of ordinal arithmetic, we can simplify this a bit, right? Uh, as I claimed before, ordinal multiplication is not commutative, right? You can't write this as 2 times omega to the omega. That would be wrong. But it is associative. So I can write this way. I can write this. I would like to get it out of the superscript, ideally. I can write this as omega to the omega times 2 omega to the omega. And now, again, like, because of the non-commutativity here, 2 omega to the omega is the same as omega to the omega. So this factor of 2 actually goes away. And this whole thing is this element multiplied by itself, which is the square of that element. And you can write this as omega to the omega all squared, ideally with the closed parenthesis not in the superscript. So here, after you have C extended everything up here, you will get a collection of this size. Okay, let's think in a different way of what is happening here. Okay, now where does it go from here? In the process of the C extension, all of the B's and A's are added and extended to everything as well. And so after this, all the A's are already added, all the B's are added, and the next thing to do is add a C into something that came uh, that came immediately after all of this. In fact, it'll be onto this one. And so the next element after the collection has reached this order type will be ACC, and then lots of more things will happen, and we can talk about C extending everything even up to here. C extending the collection of this order type. And what's that going to do? Well, there are this, not really this many elements, but this arrangement of elements, each of which is going to replicate the process of building the collection out to this size. So this is another multiplication, right? You have this multiplied by, okay, this. It's this process done this many times. I want to say this many times. It's not really, again, it's not really an amount, but it's it's helpful to think of it this way. And this is, okay, it's the square of an element multiplied by the same element. Obviously, this is just the cube of that same element. Okay. And now you should probably see the pattern here, right? We have omega to the omega all squared, omega to the omega all cubed. If you then want to C extend even this entire block, you would expect to get a collection of this order type, omega to the omega all to the fourth power. And eventually, you would expect, this will be a new page in the document here, you would expect omega to the omega all raised to the power of omega. Let me get that here. Okay, what does this mean? This can be reduced a little bit. There won't be much weird ordinal arithmetic here. This is just the ordinary laws of exponents. Because if you have a to the b all raised to the power of c, then that's just a to the b times c. All right, and that is true even for these weird ordinal numbers. So this all becomes this omega gets brought inside and becomes a multiplication, right? And we get the funny little thing here in the superscript. I'll actually write this as a chain of equality. That makes more sense. Man, even the equal sign wants to get into the superscript. And this is, of course, equal to, let me paste it one more time, omega to the omega squared. All right. Cancel superscript, put that there. Yeah. So, importantly, this is much larger than this. They look very similar, but the parentheses are in the place here to make the base large, and the parentheses are here to make the exponent large. And this is a representation of a much more complex arrangement of these elements. It's not really any more of them. In fact, I think I'd like to make that point in detail now. If you wanted to consider, even just from the original Hyperwebster, every finite sequence of letters, there's a very simple way to do it. You just consider them in order of size. You list all the one length elements first, then all the two length elements, and so on. And the list of that would look like, I'm gonna get some more space here, would look like A, B, C, and so on, Z, and then A, B, and so on. Eventually ZZ. Right. The number of things here is 26. The number of things here is 26 squared. The number of three-digit or of sequences of length 3. These are not digits, although you could rephrase this in terms of base 26 numbers if you really wanted, but that's not the statement of this, so that won't be what it is for us. But um, and you can reach any string in a finite amount of time going through the order in this way. The next string would be AAA, and then probably AAB, right, and so on and so on and so on. But these and so ons don't really represent an infinite number of steps of iteration as they were doing for us down here. These are honest to goodness finite jumps of time, and you can get to a string of length k in at most, let's say like 26 to the k plus 1 steps. All right? If you have the string of k z's all in a row, then that'll be the I believe that would be the 26 to the k plus 1 minus 1 element of this line, and you'd eventually get to the whole and you can describe the whole sequence like this. So the the cardinal number of elements here is just the smallest infinity, the countable infinity, but it's the arrangement of them in this way that I want to analyze, and these numbers are representing the the structure of that complex and beautiful arrangement. So let's keep going with this, and let's try to make this a little more rigorous, because if we keep going like this, we're gonna go crazy looking at A's and B's and C's, and it's gonna be really hard to see what's happening. So let's try to describe this in a little more of a rigorous way. Okay. Where's the top of the page here? Here we go. Let's re-examine a little bit of what we've seen here. So these things ended up being deleted in service of compression into here, but when we talked about C extending this entire collection, the effect of that was to multiply it on the right by omega to the omega, and that was the same again and again. If you, well, it seems anyway from this pattern that C extending a particular a constructed collection of the type that we've been constructing has the effect on the order type of right multiplication by omega to the omega. Okay, and I'm going to want to introduce some notation to be able to talk about this on the page and not just with a lot of words here. So we have C extension being right multiplication by omega to the omega, or so it seems, right? Now, if we go back to when we were B extending things, right, we said, okay, well, I'm going to take everything up to this point and continue the construction until a B has been added to everything here. I want to B extend it, add a B to everything here, continue the construction until that has been accomplished. And that resulted in this collection, and that had the effect of multiplying the order type by omega. As it did again when we wanted to B extend this whole constructed collection, that had this effect. It it multiplied it by omega, or wait, no, yeah, I'm I'm messing up here. This part of it was just another copy of this part. It's just this part multiplied by two, but be extending this whole collection yielded in the collection of this size all the way down here, omega cubed. So again, that seems to have the effect of right multiplication by omega rather than omega to the omega. Okay. Now, can we interpret a extension in this way? Well, yeah. So if you take a set, I'm going to bring this down here so even the empty string is on the same page as everything else. If you take this and say, okay, this set has only one element, its order type is 1. You say, okay, I want to A extend this set. I want to continue the construction until an A has been added to everything in here. Okay, well that only takes one step. That's just this, and then the collection is the empty string and A. Great, the A extension is done. That increased the order type by just 1. And that is going to be the case uh, in general. If you want to even take a larger set, like, all right, take this whole set, well, actually, A extending it is kind of pointless because everything in here has already had an A added to it in the process of creating this collection. So, but you take a set like this, which has order type omega squared plus 1, right? You say, all right, continue the construction until everything in here has had an A added to it. Okay, well, for this part of it, it's already all done. Like everything in here has already had an A added to it, and this is the only thing left. And here it is. It's just this one. It's just one more. So A extension has the effect of adding 1 to the order type. Okay, let's see if we can make this more rigorous. Let's see if we can make this more rigorous. I'm gonna bring in the rule here. The the terms that I'm going to define here are just exactly what I've been talking about, but laid out more formally. So here it is. It's in the same kind of language as the definition of the construction of this whole collection. So, given a set HR for Hyperwebster reduced, constructed under the rules we've been following, and a letter of the alphabet represented by beta, beta extension of HR is what we've been talking about. The beta extension of HR is the set resulting from continuing the construction until the next step would be to append beta to an element after all of the elements in HR. Okay, now let's go back and make sure that this makes sense with how I've been talking about it before. So I take this whole set and I say, okay, B extend this whole set. What is the resulting set after B extending this set? Well, it's to continue the construction until you would need to append a B to something outside of this set. So all the way here, it's not done yet because we aren't yet needing to append a B to something outside of this row. We've just appended it to here. It's not done even after all this because now you can apply it to you can add a B to this element. It's not done yet after this because you've applied a B to this element. It's only done after all of this because then the next step after this would be this one, and that would be to add B to this element, which is not in the original set under consideration for B extension. Okay, so this kind of makes sense with what we've been talking about so far. So I'll write this as a function, beta of HR. It's a function from the power set, which is the set of all subsets of HR, the big HR, the entire reduced Hyperwebster, if we ever get that far, which I promise we will eventually. It's a function from the power set of HR to itself. It takes one of these constructed subsets as an argument, and it outputs a different one as its value. Okay, what can we do with this? What can we do with this? So, I want to let's consider some very simple examples using this notation. So, A of the set containing the empty string end set end function. What is this? Okay, this means to continue the construction of this set containing these elements, in this case only one element, until an A is going to be added to an element not already in here, at which point the construction ends and the function is evaluated. It returns its values. So the value of this function is a set. It's a subset of big HR, and it's to continue the construction of this. So it obviously starts with this, and then what's the next step? Well, we should be pretty familiar by now. The next step after empty string is A, and then we're done, right? Because the next step would be to make AA out of A, but A is not in this argument set. So this is finished. The set is complete, and this set is the value of this function. Okay. Okay. What about? Okay. So you take your a function, but then put in this set again as an argument. Well, this is the same as applying the a function twice on that same set, right? Which, using the standard function composition notation, should be written as a squared of this set. And this, again, is very simple. You continue the construction on now this set until you would need to append an A to something not already here, and then it's done. And just writing that out very explicitly, that is the set containing the empty string and A and AA, right? You've appended A to this, creating this. This is allowed, but then to construct just one more element would be too much, because that would be adding an A to something here, which is not in the argument set of the outermost A function. So this set is done. Close brace. Okay. So that's how this notation is going to work. And I'm going to want to talk about the order type of these sets. Right? That's the whole point, is to get these big ordinal numbers like this and bask in their majesty. So how would I want to write the order type? Well, I've already whined and complained that these ordinals aren't really like the size of the collection they're describing, but they are kind of like it in the sense that we're interested in. So I think it's kind of appropriate to use the absolute value notation when talking about this. So if I want to assert that the order type of A of a set is just the order type of that set plus 1, here's what I want to write. I have this written somewhere else in my notes. Here it is. It's that the order type of A of a set is just equal to the order type of the original set plus 1. And now this is written very nicely and compactly, and they don't have to use a lot of words trying to describe it and like losing people that might be listening. Okay, so here it is. So, what would this relationship look like for the b function of the b extension? Well, let's see if we can get a handle for that. What would be of the very first and simplest set, the set containing the empty string? What is this? So, continuing the construction up until you need to add a b to something that isn't in here, well, continuing the construction would look like empty string a, and so on. All these finite strings of a's, and then after all of this, you'd want to add a b to this first a, right? Because you're not supposed to extend the empty string until you can't do anything else with anything else in the set so far with that particular letter. So if you would want to write down, okay, BA, but now this is too far because according to this definition of this function, you only want to continue constructing this collection out until you would need to add this letter to something not in here. And that's what this would be. So you don't do this, and the set is done, and this is the value of the function. And what is the order type of this? Well, the order type of this, which is omega. That's not what was in my clipboard. Hold on. There's got to be an omega around here somewhere. There is. This order type is omega. So notice how we took a set of order type 1. We b extended it. We got a set of order type omega. Okay. This should be pretty darn similar to the pattern we were observing before. I claimed that b extending a set was the same as right multiplication by omega. This is consistent with that pattern, right? Because 1 times omega is the same as omega. So now, I mean, we already talked about this before, but we can do it in this notation now, right? Because now b of this set, but I guess now I'll write this as b squared of the set containing the empty string. This is equal to, well, it's the b extension of this set. So it's to continue the construction until you would need to add a b to something that isn't in here. Well, we already looked at that. That was up here. And you only need to add a b to something that isn't in here when you get all the way out to here and have created a set of order type omega squared. So the order type of this set, of the set resulting in the evaluation of these functions, is omega squared. This is restating what we observed before in this nice notation. So now if we want to make a claim like this, what would that look like? Well, it would look like this. It would look like this. Is that the order type of the b extension of a set is just the order type of the set in consideration, right, multiplied by omega. Right? This is exactly what we observed before, just now nicely written like this. And now we can do the same thing for the c extension. If we just are translating our previous observations into this notation, it would be that the order type of the c extension of a set is just the order type of the original set multiplied by omega to the omega on the right, specifically on the right. That matters with ordinals. Okay. Can we generalize this? Because it took us a long time to get all the way up here. And we might not even yet be convinced that this is the case, right? I had to take some pretty wild leaps in logic to make these kinds of claims, and yeah, that's fair. It definitely was that. I will admit it. So let's try to think about this now more recursively, and if we can do that, if we can establish a base case like this, and then like a recursion relation, like on the letter being considered here, beta, then maybe we can hope to jump all the way to the end of the alphabet in a very few steps. And then that'll be the end. And that's pretty exciting. So, let's think about this in that way. Let's give ourselves some more space here, and let's just go back to B of, well, ideally not all the way up in a superscript. Let's go all the way back to B of HR. What is this doing? How is the size of this increasing as the construction is being done on the set HR? Like, what does that look like step by step? All right, so at each step in this construction, right? Let's use this one as a concrete example. All right. At each step in this construction, an A is added to something that is previously there. Right. That's what this function now does. And as it does, each time the order type increases by one. Now, the if you were to do if you were to go this far, this would be a of the empty string. So this far would be a squared of the empty string. To go this far, it would be a cubed, and so on. You can imagine the the number of composed functions of a is going all the way to becoming omega in the limit. All right, that's the kind of thing that we should be pretty familiar with by now. So, if we have something like this, right? It's the limit as n goes to infinity of a applied n times on the, well, in this case, it's not the specific empty string set. It's the general set HR, and then this, you want to say it's the order type of this thing. It's just you imagine applying. Well, you imagine A extending this set arbitrarily many times. In fact, infinitely many times in the limit, right? And the order type of this, of the end of this process, of the limit of this process, is the order type of the set given here. One of these absolute value bars ended up in the superscript again. they're always trying to get up there. Okay. I hope this makes sense with what I've described, because it's pretty important to what we're going to be talking about again going forward, right? A a a squared of the set containing the empty string is this set here. A cubed would be to add one more element onto this set, and if you were to continue that process arbitrarily many times, infinitely many times, you would get this set, which has order type omega. That's what we say is B of this particular set. It's true of every one of these constructed sets. Okay. The limit of this sequence here. This is like a sequence of, in general, ordinal numbers. In this case, it'll be just natural numbers, because the order type of these sets. Well, no. In general, like this is not specifically the set containing the empty string anymore. For a general set, this is the limit of a sequence of sets, and it's the limit of the order type specifically of those sets in sequence. I'm sorry, that was a little confusing. It's a sequence of numbers that looks like, especially if this is the empty string, then the sequence is one. That's the order type of the set containing the empty string. Two, that's the order type of the set containing the empty string and a, and three and four and so on. And the limit of this sequence is just the limit as n goes to infinity of n. And if you've worked with limits at all, you would recognize this. Of course, this is going to infinity. Now, when we're working with ordinals here, as we are liking to do, then I would prefer to write this as omega. So, this is like doing the plus one operation omega times. Again, not really appropriate to use that to describe an amount, but it's really so similar. It's really so similar that it's good enough, at least for my purposes here. So you apply the function that adds one omega times, and as a result, you've added omega. Now we claim that the b function is like multiplication by omega, but uh, that is just because in this very trivial case, the order type of this original set here is just one. For a more general set, you would have the order type of this set in here being multiplied by omega. Be extending this this whole set, is to add a b, or it's a continue the construction until you want to add a b to something that's not yet in here, and that takes until all the way down here to get there. That is indeed that is multiplication by omega. It's not merely adding to it. If you want to b extend only this little set, that only requires you to go this far. Now that looks like it might be the addition of omega, but remember, the order type of this set is 2. There are 2 elements in it. Okay? I'm very happy that this has worked out. I was afraid I may have made a mistake here, but no, it does work out. The order type of this set is 2, and b extending it takes us all the way out until you want to add a b to something isn't yet in here. Here's fine because a is in here and ab is the extension of that. All the way out to here, and you don't add this one. Omega 2, it's multiplication of 2 by omega. Okay, very good. It checks out. It checks out. And I haven't proven it. Again, I haven't proven it. I do not have the capabilities to be able to prove this, but in the few examples that we're looking at, it seems to hold. I'm pretty confident that this holds in general. So let's move on a bit. Okay, so we've realized that the b function is just the limiting sequence of applying the a function arbitrarily many times. Okay, so now we want to observe that the c function is just the limit of applying the b function an arbitrarily it's not really how grammar works, an arbitrary number of times, also known as arbitrarily many times. So we want to write this, that the order type of the C extension of a set is the limit of repeated B extension of the same set. specifically their order types. Do we believe this? Do we believe this? I, I invite. I'm not going to do this again, just for the sake of excessive repetition. But in the same way, going back and checking that this makes sense on B being a repetition of A, this makes sense thinking of C as repetition of B. And now we are really cooking because the B extension on a set was found to multiply its order type by omega. Multiplying by omega arbitrarily many times leads, of course, to multiplying by omega squared, omega cubed, all the way out to omega to the omega. This is what we observed before again. This is all lining up, and so now that we've observed this pattern going from A to B and from B to C, I think I'm ready to apply this again, going from C all the way now to D, a letter so far unheard of in this construction. But if we believe this, then its effect on the order type is simply to apply C's effect on the order type arbitrarily many times. And in the limit, what would that be? Well, it'd be omega squared times, or it'd be omega to the omega times omega to the omega, which is omega to the omega all squared, and so on and so on and so on. And we saw that up here. That leads to omega to the power of omega squared all in the exponent. Okay. So now we have something. How are we going to write down this beautiful result in more general terms, right? Because of course that's what we want. So let me grab that here. In fact, here let me actually grab this. I went to all the trouble of writing this down. This is I think worth seeing. This is what I've claimed before. It's the limit of this sequence of order types. You multiply by omega. That is one application of B. By omega again, that's another application of B, and so on and so on. In general, you've multiplied by n applications of B, which is to multiply by the omega to the n, and in the limit, it's multiplication by omega to the omega. Okay. How does this apply generally? Well, let me now actually write out what I just claimed before. It's the limit of this sequence of ordinals. The order type of the original set, the order type of the original set times omega to the omega, times omega to the omega squared, and so on and so on. And so the effect of de-extending a set on the order type is to multiply it on the right by omega to the power of omega squared. And we didn't have to write out a bunch of elements anymore. We just observed this kind of relation, and now it's like I said. Now we're really cooking. We're almost there. let me plop this beautiful statement down here and see if we believe it. In general, for the kth letter of the alphabet, alpha k, recognizing that in the base case, k is 2, because of course we don't have this this pattern. Also, I'm realizing this. I've written. Oh yeah. In the base case, which is k equals 2, because for the second letter of the alphabet, b of hr is the multiplication by omega to the 0. Omega to the 0 is 1. Omega to the 1 is 1. This is multiplication by omega, as we observed before. And it doesn't really work for a. Like you can't write like -1 here. Omega to the -1 does not really have a meaning that is useful. So, and so the base case will be k equals 2, and we have this beautiful statement. Oh, isn't this gorgeous? So many so many symbols here. Alpha k extending, right? We have A extending, B extending, C extending, and in general, alpha k extending, the kth letter of the alphabet, of the constructed set HR. The, the order type of that is equal to the limit of these order types. It's the order type of just HR times omega to the k minus 3, or the not omega to the k minus 3, omega times k minus 3. Here's where exponentiation comes in. Omega to the omega k minus 3 all squared, omega to the omega k minus 3 all to the n in general, and the limit of this is omega to the omega k minus 3 times omega. The omega gets distributed in here. We have k minus 3 copies of omega. We have now one more. There are now k minus 2 copies of omega out here. And the effect of that is multiplication of this by HR, the constructed set for k greater than 2, because this pattern does not hold for the very first letter A. So, what is the conclusion here? We want the whole reduced Hyperwebster. You want the 26th letter, right? So, not quite. Not quite. Because if we plug Z into this, that is the construction up to the point where the first Z would be included, but stopping before it would actually be included. So, in order to answer the final question of what is the order type of this whole reduced Hyperwebster, we'll like imagine a 27th letter of the alphabet and plug that in, and we will consider if we want to represent the mysterious 27th letter by the capital Omega on the empty string. And this would be to continue the construction until you would want to add this letter to something, but not actually doing it, which is what we want. Because the result of that is to go through the construction until you can't even append a Z to create anything new. Everything has already been done, even on the empty string, right? Even on the empty string. And now, because of the empty string, well, I'll get to that in a moment, because first we want to have our big triumphant moment of the final answer, right? So plugging k equals 27 in here, and the order type of the set containing just the empty string is 1. We have this expression as the final answer. All right. And we've plugged k as 27, so this will be omega to the 25. Now this is great, right? This is awesome. I'm now going to slightly ruin the moment by saying it's actually all this times 2. I hate to do this. I really hate to do this. This shouldn't be in the superscript, but because of the empty string, as it was for this case, when we wanted to get this whole set going, and we got to the point where we were finally done adding B's to everything here, we also needed to add one here. We had to duplicate the entire thing with a B in front. The effect was to create 2 copies of the same structure. That is still true here. The reason I hate to do this is because this is not reflected anywhere in these expressions up here, but I could not for the life of me get it to make sense with this factor of 2. I'm sorry. I recognize it casts a bit of doubt on everything I've done. I will just have to accept that. I maintain that this answer is as good as I know how to get. If anyone can do a more thorough analysis I would love that. I would love to see a more thorough analysis of this and get a better answer. Maybe this is even wrong. It's entirely possible this is wrong. But this is my this is my result. And the final order type of this reduced hyperwebster constructed under these rules, all this, the order the order type is omega to the 25 all times 2. There we go. That's it. That dang empty string though. It ruined the fun at the end. I think it was worth it, but if we had left the empty string out and we had insisted that the first element is A, then we would have never gotten anything except strings that start with A, because the construction is is such that you only add a new element to the collection by adding to a previous element. So if the first element is A, you won't ever get anything except things that start with A. Now, if we had done that, then the cool thing would have been that then at the very end, we could have just said, okay, now now take the A away from all the elements. Take that first A out of every string in which it appears, which is all of them, and then the resulting collection will be the entire reduced hyperwebster thing again, right? That's what the hyperwebster is kind of known for. Is that if you have this, if you consider only the if you consider only the strings that start with A, and you take away the initial A, and what do you have left? You you have the whole thing, right? You have all the strings that start with B and C and Z. You have all of them. So maybe it would have been even cooler to do it that way, and then at the very end, you pull the final rug out from underneath everything and say that, aha, even though all we've built is things that start with A, really it contained the whole thing the whole time. So, I don't know. I'm not going to do this again with that in mind. There we go. There's the. That's it. Final answer. Oh, man. So, my closing thoughts on this. I already kind of hinted before, but I really do believe that this collection does contain every finite sequence of the that can be made with the 26 letters, and it's the same reason I had before, because it definitely contains all of the one letter strings, and then just by process of adding on to previous things, it will eventually get all of the two letter strings, and then eventually the three letter, and so on. So I really do believe this does contain all the finite strings, so I'm pretty happy with that. And I'm even more sure that everything in here is unique, because it's a very explicit part of the construction. An element is only added if it's not already in the previously constructed set. So yeah, I'm convinced that all the finite strings are in here, that they're in here exactly once and only once. Again, I can't really prove that, but I really do think that's the case. um, so yeah, about this number. Um, when I started this, I was thinking that maybe the order type would go all the way like to epsilon naught, right? Let me write that quickly. I have that copied down somewhere. That that letter. Hold on. I thought the order type might go all the way to this ordinal after the first few letters introduced, and then not really make any more qualitative jumps after that. Um, but then, as I was starting to get a feel for the structure of this thing up here, uh, I was afraid it might not get past like omega to the omega like 26. Like even here, Well, actually, here we'd already reached omega to the omega squared, but yeah, I was thinking that like wow, it might not even get this far. So I'm kind of happy it settled around this number. I'd been kind of hoping for actually. Let me I'd been kind of hoping for something more like this, honestly, like omega, like and then these Knuth up arrows, 25. If you know this notation, this is meant to represent a an exponent power tower of omegas that is 25 omegas tall. I'd been hoping it would be that. I would think that would be pretty cool. And then if you were to consider an alphabet with arbitrarily many letters, then the limit of this, it really would be epsilon naught, and that would have been neat. But I'm pretty happy with this overall. I'm happy that I was able to actually conduct this analysis in a way that made sense, at the very least to me. I hope anyone else that watches this, it made sense to them as well. And yeah, I mean, I gotta say, what I'm most proud of is this ordering here. I was really worried when I realized that alphabetical ordering is not a well ordering, and I thought maybe this whole idea was kind of like dead before it even got off the ground. But no, I made the commitment to come up with something that makes sense and produced something that in the first stages looked very similar, and it really worked out. Just following this really led to some good things. It got the final answer. Assuming I didn't make any mistakes, which again is possible. This wasn't done in a truly rigorous and formal way. Again, I'm at best an amateur mathematician. But yeah, this was very fun. I hope that there is someone who gained an appreciation for the complex structure of these ordered sets with these weird and funky order types, and how the structure just explodes and expands and stuff, like even on a set which doesn't have any more elements than there are natural numbers, right? If you just arrange them in a simpler way, there are only just the basic, uh, countable infinity number of elements here. So, but if you insist on arranging them this way, this is a really cool exercise in appreciating the size of ordinals, I feel. So there we go. That's it. Hope you enjoyed.